thank you guys for first inviting me to come out there and then for asking me to give this talk. So today I'm going to tell you about super heavy dark matter, mostly thermal dark matter. This is based on a bunch of papers and work in progress with my two students. Let me go quickly. So what are thermal relics? So a thermal relic is a relic particle that was in equilibrium in the universe. It went out of equilibrium and has an abundance right now. And so why do we love thermal relics so much? Well, because they're very simple and they're predictive. There's some interaction in the universe that keeps it in equilibrium, let's say some coupling with the standard model bath. And so therefore, once it goes into equilibrium, it's completely insensitive to all the initial conditions. And then when this coupling becomes weak, when this rate becomes weak, it freezes out, it goes out of equilibrium, and the abundance is set. And so this also tells us maybe how we look for the dark matter, because when I calculate its abundance, it tells me what the interactions are with the standard model, and it tells me how I can discover it. We also like this because we've used this exact same thing to determine things like the helium abundance or the free electron fraction. It's the same thing. If things were in equilibrium with the bath, they went out of equilibrium, and the physics is in when it comes out of equilibrium. And so this idea of a thermal relic has been a big motivation for our theory and our experiments. So one big thing is the WIMP. So we focus a lot on the range between 1 GeV to a TeV based on the WIMP miracle. And if we expand what we thought a thermal relic has been for a while, it's somewhere between what the BBN sets the bound to be and what's so-called the unitarity bound in 10 to the 6 GeV. And now I'm going to talk about how we take normal, predictive, and simple thermal relics and go beyond these bounds. There's been work going below the BBN bound all the way down to the warm dark matter limit. And I'm going to talk to you more about how we go beyond the so-called unitarity bound and go all the way up to close to the Planck scale with a thermal relic. And so where does this unitarity bound come from? So basically, like I said before, there's some 2 to 2 annihilations into standard model. These are going fast, back and forth fast in the universe. And at some point, they go out of equilibrium. And so you can calculate the abundance just basically calculating what was the rate when this thing went out of equilibrium and what was the amount of dark matter when that happened. Now it'd give you a relationship between the dark matter mass and the coupling needed to give the right abundance. And if you parameterize the cross-section as some coupling squared, alpha squared over dark matter mass squared, you find that the correct abundance goes like m dark matter is equal to this coupling times 30 TeV. And so we see if you put like a weak coupling, we get the weak scale. And so the unitarity bound, essentially that we take the largest perturbative coupling that we can think of, alpha equals 4 pi, and we see that there's a bound of dark matter for this type of process around a few hundred TeV. And this is a so-called unitarity bound. And this has been kind of like a very strict bound for a pretty long time, up until the last couple of years. And so what exactly is happening? So the rate for which dark matter to annihilate and stay in equilibrium in your universe is proportional to the density of dark matter. Because if you're a dark matter particle and you want to annihilate yourself, you need to find another dark matter particle. And so why does this lead to a very strong unitarity bound? Well, because a dark matter particle eventually becomes very rare. Because as the dark matter becomes non-relativistic and stays in equilibrium, its density becomes Boltzmann suppressed, because very unlikely to find a dark matter particle. And so eventually this process just turns off and the dark matter abundance is set. And so this is a limiting factor to how efficiently dark matter can annihilate itself away and lead to heavy dark matter. And so the very simple way to just think about how you go beyond this unitarity bound is think about dark matter scattering off something that's very abundant. So if dark matter annihilates through finding another light particle that is abundant, then this rate can be very fast. It can very efficiently annihilate away the dark matter. And so if it's a very small number density of dark matter, that means the dark matter mass must be very large. So this is basically the very simple thing that I'll use to show how you can get very, very predictive and very simple models of dark matter that goes well beyond the unitarity bound without going to a non-standard cosmology or something like that. So the first example I'll tell you about are what we call zombies. And so here are zombies. So suppose, so DM is a dark matter. This Xi is what I'm going to call a zombie. So a dark matter finds a particle Xi and annihilates into 2 X's. And we call this a zombie because essentially what happens is this dark matter finds a zombie, the zombie bites the dark matter and turns it into a zombie. And so you first think about, you see this process, well, if the C is going to be lighter than, so if we want to go beyond unitarity, and if you want the dark matter to annihilate something fairly efficient, then we want the dark matter to be heavier than the zombie particle. And so that's one constraint if you want to go beyond unitarity. If you're not interested in going beyond the WIMP unitarity bound, then this constraint is not necessary. But however, you immediately notice that if this zombie particle is lighter than the dark matter might just decay to 3 zombie particles. And so in order for this to be a dark matter candidate, it must be the dark matter mass must be less than 3 times the mass of the zombie. And so the dark matter, so we want to calculate the relative abundance. So I've decided to do my first n-body simulation on calculating this dark matter abundance. And here it is. And so here you see that the zombies are eating the dark matter, I guess the survivors, and at the end, they're mostly zombies and very unhappy dark matter particles. And so here's a very simple model of this. So there's some Yukawa coupling between some scalar that mediates the zombie process. There's we just charge this zombie under some U1, let's say a U1 lepton or U1 B minus L or something similar. And we can go ahead and solve the Boltzmann equations, even get a good analytic estimate for what the solution to the Boltzmann equation is. But I'm not going to go into that because it's a short talk. And what you find is a simple phase diagram like this. So here is some coupling that the details are important, that parameterizes how fast the zombies annihilate into center model. Here's some coupling that controls the rate of the zombie process. And you see for, let's say, for very small couplings of 10 to the minus 2, 10 to the minus 3, you get fairly heavy dark matter, not compared to the WIMP. But even for parameters within unitarity bound, so for instance, couplings around 10 to the minus 1, you can get dark matter well beyond the standard unitarity bound, or 10 to the 8, 10 to the 9 GeV. If it's okay, also if you take parameters higher, at some point these zombies will dominate the energy density of the universe to become matter dominated, and you can get even heavy dark matter in these scenarios. And so the problem is, as you might see, that these zombies are very close to mass with the dark matter. And the dark matter is beyond unitarity bound. So the zombie mass is beyond unitarity bound, but it's annihilating through zombie go to 2 center model particles. So this zombie particle has a unitarity bound problem. It's always going to be overabundant. So the zombie must be unstable. And that always leads to the fact that the dark matter is unstable. And I'll give you another example of this. And actually, this is a generic prediction of thermal heavy dark matter, that the dark matter is always going to be metastable. So let me give you another example. So chain dark matter. So here we consider a chain of dark matter. So dark matter comes in different flavors, 1 to n, and it scatters or co-scatters off the standard model path. So chi1 will be a dark matter candidate. It can turn into a chi2 can turn into chi3, and so on. And so each one of these processes is very efficient because a light standard model bath particle is very abundant. So when dark matter becomes non-relativistic, this thing is not becoming exponentially rare. It just has redshift slightly. And so this process is extremely, extremely efficient, and we hope to get heavy dark matter out of this. And we would require that the last particle in the chain does decay directly into standard model particles. So this way, there is a process that reduces the total number of dark matter flavors. Now, why do we need a chain? Why not just start with one process, just one co-scattering process? Well, the problem is the same as before, is that if you just have this process, then I can take these standard model particles, bring it all to the right side of the diagram, and the dark matter is unstable. And so even though this will predict a chi1 that freezes out with a huge abundance, it's going to decay soon afterwards. And so this very long chain allows this dark matter to be quite metastable by introducing a very large phase space for the dark matter to decay. And so, okay, so I can't go into and show how you solve the Boltzmann equations, but I'll give you just a quick flavor of what all the numerics are. So let's just consider this two-chain process and somehow think magically the dark matter is stable. So if you go ahead and calculate the abundance for some cross-section, it's just basically 1 over the dark matter mass, you'd find you get the relic abundance for dark matter mass is 6 times 10 to the 14 GeV. Okay, so if it takes extremely heavy dark matter, it's completely thermal, and its couplings and its relic abundance is determined just by its couplings to the standard model. So it's very predictive. Obviously, we have to go back to the chain. And so one way to think about this chain is think about it as actually a random walk, where on the left side of the chain, dark matter hits a wall. The right side of the chain, it decays and falls off a cliff. And then if you want, instead of solving the n Boltzmann equations, you can just solve one diffusion equation and get the answer for the relic abundance. And again, I'm happy to talk more about details, but since it's a short talk and it's late, I didn't want to go into it. And so here is a plot of n being the number of particles in the chain needed to make the dark matter metastable. And so look at this green curve here, this purple curve here. And here's the mass of dark matter. And here are some couplings for 2 different models that we had in our paper. So you see that for large couplings, the dark matter mass can be well within 10 to 13, 10 to the 14 GeV, well beyond the so-called unitarity bound around 10 to the 6 GeV. Still trying to think about how to get all the way up to the Planck scale, and we have some ideas. And so in both cases, I want to point out that they gave you nearly degenerate dark sector states and a metastable dark matter. And I'm going to be showing in the paper now that this is actually, you can actually prove that this kind of has to happen, like a physics proof, because the idea is simple. In each case you saw, they need a dark matter particle to be roughly close to mass with it. If there is, that particle itself will have a unitarity bound problem if it's that mass, because it'll be overabundant. And so therefore, that particle needs to decay away. Maybe that particle talks to another particle. Eventually, you get to something has to decay, and you essentially make the dark matter metastable. Again, I'm happy to talk more about this work in progress too. It should come out in a month or 2. And so I hope I at least convince you somewhat that thermal heavy dark matter, well beyond unitarity bound, is possible. It's interesting, but most important thing that we should think about how to find it, because it doesn't give the same signatures as a standard WIMP that we can look for in jet detection and so forth. So now my third example. It's funny how you told not to talk about more than one thing in the talk, but I guess since it's 20 minutes, I can talk about 3 things. This final example is something called squeeze out. And so here we're kind of motivated by simple theories, not let's say simple setups. So here consider just a very simple theory of a confining SU3 strong force with 1 flavor. Okay, and let's take the quark mass to be much heavier than a confinement scale. So it's a very simple theory, just 1 flavor of heavy quark in SU3 theory. It doesn't have to be SU3, it doesn't have to be 1 flavor, this is just the simplest. And so this is atomically free, we have bound states, we have mesons, we have baryons. We'll think that baryon symmetry protects the baryons, these would be our dark matter candidate, and these mesons are unstable and they decay. We're agnostic about how it couples to the standard model. And so let's again, I'm motivated by looking for ways to understand heavy dark matter. So let's consider this dark matter as heavy. And so it's annihilating to 2 gluons as a squeeze-out process early on, and it's going to be overabundant if it's heavy. So this is not the end of the story. Because the quarks are not the dark matter, the baryons are the dark matter. So you have to understand how these quarks turn into mesons, how they turn into baryons. So you have to understand the physics of the phase transition. And so here's the first stage. Oh, look, there's another n-bias simulation. So here are the quarks and antiquarks. They've frozen out after some large abundance, but they're too far apart to recombine. As we know, recombination doesn't happen right away. At some point around the critical temperature, around the confinement scale, you start to nucleate bubbles of the confined phase. And they start to populate all over. And you can calculate what is the initial size of these bubbles, but they don't really play a big role, and neither does the nucleation rate. Just need to know that the nucleation rate is fast. Okay, and at some point, so these bubbles nucleated and they're starting to grow. If they're above a certain radius, they'll begin to grow. And soon these bubbles will collide, and they'll begin to coalesce. And so at some point, as we described, you'll reach a point in which the rate for the bubbles to coalesce is fast, and the universe is built mostly with just bubbles that are fast enough to coalesce. And so this is some characteristic radius we'll call R1, which I calculated to be m plank to 2/3 over t critical to 5 halves, but it's not important. Just know that you can roughly get an estimate in which the universe is half filled with these bubbles of this size. And if you want it the opposite way, the universe is half filled with pockets of this size. So we have the universe filled with large bubbles of the confined phase, or large pockets of the deconfined phase with the quarks still sitting inside, because the quarks haven't passed through these bubbles yet, these bubble walls. And so now look at this picture where I have these contracting bubbles with these confining phase bubbles pushing into the deconfined phase, and these quarks are bouncing around inside, and they can't go out of the bubbles until they've hadronize. It's not like the standard model where there's a light quark where you can just pop out these light quarks out of the vacuum. You can't really do that because these quarks are very heavy, and the rate, to pop out a very, very heavy quark antiquark out of the vacuum for this to leave the deconfined phase is very, very rare. And so what happens is these bubbles start to contract these quarks and antiquarks. At some point, they contracted so much that they begin to cause hadronization. So they begin to form into baryons and mesons. Okay, so they're bouncing around. At some point, they're going to form into baryons and mesons. So what happens? They form into baryons and mesons, and once they form, these baryons can escape the pocket, and the mesons, they just decay away. And so the relative abundance of dark matter is just going to be determined by what is the amount of baryons that are squeezed out of these pockets. And we've done some calculations, including the hadronization rates, the pressure of the quarks on the wall, the speed of the walls are contracting, the speed of the baryons inside. What's important is if the process is slow enough to find that the system will equilibrate. And essentially what would happen is you annihilate away all the baryons and antibaryons in the pocket, leaving nothing left over. However, just from pure statistical analysis, there will be an excess in each pocket of baryons or antibaryons, just from a pure, just random, just from normal Poisson distributions, Poisson statistics. And so what we showed is that the contraction is slow enough to essentially annihilate everything away except for some accidental asymmetric component in each pocket, which is roughly the square root of the number of quarks in each pocket. Oops. So all we need to know to find the relic abundance of the baryons is what was the average size of the pocket when they started to contract. And that was this value R1, which was what was the average size of the bubbles or pockets when the coalescing was fast. And so what you find is that this very efficiently annihilates away all the quarks, except for some accidental asymmetry that sits in the pocket. And so just to show the whole picture again. I didn't realize that I had this slide. Oops. Okay, fast forward. And so here, for SU3 case, one flavor, we solve for the relic abundance versus the quark mass over confinement scale versus confinement scale. And here are contours of constant dark matter mass in units of TeV. So you find that roughly this predicts around dark matter mass around 10 to the 5 TeV, so around 2 to 3 orders of magnitude beyond the so-called unitarity bound. And it's just a very simple model of a confining sector with heavy flavors. Oh, that's it. So I hope I convinced you that heavy thermal dark matter is interesting, that we should look for it, and that it's fun to do. Thank you.
Thanks, Eric. Questions?
Hey, Eric, it's Jeff. So you were saying initially, or not initially, in the middle of the talk, that there was a theorem that dark matter evading the unitarity bound means it's unstable. But is that really the case for this latter model here? Is it unstable for some reason?
No, it depends if you want to call this thermal or not. I think that would be the thing. I mean, I guess it does remain in equilibrium with the pocket. So it's just a physics proof, so there are exceptions. But that's a good point. I wasn't really considering this to be thermal. As really the question, actually, I really should state this as a theorem with a perturbative unitarity. So once I go to non-perturbative physics, these can be evaded.
Okay, thanks.
Yeah, I should have said that.
Hi, Eric. It's David.
Hey, Dave.
Hey, how's it going? Listen, so I had a great time reading this paper when it came out, but there were two questions that I had in my mind, because in my mind, this is sort of a Looney Tunes cosmology where these heavy hadrons are bouncing into the bubble wall and they try and go in and then they get snapped back because they're so heavy that having them penetrate would be too energetically expensive. At what point do these dark quarks become so heavy that the back reaction of them hitting the phase transition wall actually arrests the phase transition? Is there any feeling for that?
Yeah. So so they definitely create a pressure that slows down the wall, which only increases the ability for baryons and antibaryons, the ability for quarks and antiquarks to annihilate inside. At some point, actually, we think now that working with Dilu and Jan, I can't pronounce Jan's last name, but I think he's in the audience, that actually it might be the case that the pressure becomes so large that it would push against the wall to start expand, and then it will come back and contract, but still it wouldn't change the result so much because you just left up with the asymmetric part in the bubble at the end.
Okay, and I guess as the universe cools, eventually the phase transition has to proceed no matter what. But okay, so the other question I have is how, in your plot, you show the range of m over lambda of 10 to the 2 to 10 to the 5 or so, if I recall.
Yeah.
So what happens on the other end? Like, can you make this mechanism work for mq over lambda of 10? Like, where does that stop working?
Oh, it stopped working because there are some issues that makes it hard to calculate. First, you could have recombination before the phase transition. So you could start forming baryons and protons. You could start forming protons and mesons before the phase transition happens. That is a complication I just didn't want to deal with.
I see. Okay, so, okay, fine. Okay, makes sense. Thanks, Eric.
You're welcome.